Well, hey there, class. This is Mr. Rogers. Sorry I can't be here today, but I didn't want to let that slow us down, and I thought maybe, with all the work that we've done in the last few class periods with stars and how they work, that it might be a good thing just to kind of keep pushing along. So I thought I'd make this recording so you could hear my sweet baritone voice, and we could continue to do some more stuff with stars. So, with all of the different things that we've learned about stars, the way that they live their lives, the way how they form, how they blow up at the end, and then the cores shrivel down and make black holes and white dwarf stars and all that crazy stuff in between, I thought that maybe to kind of help organize all this information, it would be best to put it all into some sort of graphic organizer. And that graphic organizer is going to look something like this right here. So I'm going to ask your substitute to pause the video and hand this sheet out to all of you. So I'm going to let your teacher pause the video, and I'll wait here patiently. And when the papers have been all handed out and you all have one of these in front of you, then you can hit the play button again and you'll be able to find out what we're going to do next. See you in a couple minutes. All right, well, it looks like we're back. Wow, it only seemed like it took a couple seconds to me. It's amazing how fast time flies. So when you look at this graphic organizer, you might notice some similarities. For example, you'll notice these three arrows over here on the left side, and you notice how these arrows kind of lead along these series of images here, these circles, and then that little blow up thingy. And then you notice how it looks very similar to this line and how it looks similar to that line. And you might also have noticed, and I'm sure someone's blurting it out at this point, how different they are and how they're different in size. You notice how that's a little bit smaller, that's a little bit bigger, and that's the biggest one. Almost reminds me of a little bit of a Goldilocks story. And so here we are doing the Goldilocks story for the three different ways that stars live their lives. So hopefully you're ready to write things down, and feel free to pause the video whenever you need to pull it back a few seconds or a few minutes and repeat it to make sure that you've all got it just fine. So that's the beauty of this thing. If I'm going too fast, doesn't matter. You can always shut me up by just hitting a button. If only that were true all the time, right, class? All right, so before we get going, just because I can. All right, then let's move on to this right here. Now this image, you might wonder, what the heck is that? And if you've been on top of things for the last few days, you might recognize this is a giant cloud of gas and dust in outer space, and that has a particular name. It's called a nebula. Or more accurately, when there are stars forming in a nebula, we like to nickname it a stellar nursery. Now you might be wondering where on your graphic organizer the stellar nursery belongs. And if you look right here, the stellar nursery is going to belong right here. That stellar nursery is going to feed into all three of these lines. Since a stellar nursery is where stars are born, this is the path for each star life right here. So in this gap, why don't you write stellar nursery? You might even have to turn your page sideways to make it fit along here. Once you've got that ready to go, I want to point a few things out about this awesome stellar nursery. But before I do, you might be wondering about the three arrows. So let's label these three arrows too. For example, the first little arrow, the one that points up to the right, we're going to call that a 1x star. The middle arrow, the one that kind of goes right down the middle of your page, we're going to label that a 2x star. And then the third one, you guessed it, a 3x star. Now you might be wondering, what is up with the x's? Why 1x, why 2x, why 3x? Well, here's the trick. X is going to equal the size of our sun. So a star that is 1 times the size of our sun, you do the math, kids, 1 times the size of our sun is the size of our sun. And so stars that go along this arrow right here, those are 1x stars. Stars that go down the middle arrow, that's 2 times the size of our sun. Those are 2x stars. And then the arrow that goes all the way down to the bottom right, those are 3x stars. So if I were to back it up one more time and take you right back to that graphic organizer, what you're looking at then is 1x stars along here, 2x stars along here, and 3x stars along here. Hence The 1x stars are smaller, 2x's are a little bit bigger, and the 3x's are bigger than that even too. All right, so jumping ahead then again, I'm going to take you back to the nebula, the stellar nursery. And you might be wondering, are there any stars that are forming in this nebula right here? And the answer is yes. This blob you see right in front of you is a couple light years across. Do you notice that there's starlight shining from within that cloud? We believe that there is a star that is just being born inside of that nebula. The gases are condensing, gravity's pulling it all together, and once that clump of gas gets big enough and it can start to fuse the atoms together, it will start to shine with its own light. That's not the only place, though. We have another nebula right here, which is forming more stars. And believe it or not, you're seeing a star exploding in this section right here. Can you spot it? Well, I made it kind of easy for you. It's right here in the middle. There's a star that's already run through its life, even before it's left this nebula. And then, of course, we've got this beautiful piece of nebula right here. And again, you can see the gases clumping together, forming stars. It's pretty amazing to see whole solar systems forming right in front of your eyes. But we're going to go along with the 1x star variety here. And once we get through the 1x, I think you're going to find that 2x and 3x are much more straightforward and easy to do. So, what happens when you get a 1x star? Well, all 1x stars, when they form from a nebula, they begin their lives as main sequence stars. And what do main sequence stars do to shine? Well, they're going through this process called fusion. And if you recall, either from our review yesterday from the video or maybe from the video itself, fusion is when you take hydrogen atoms and you jam them together to make a bigger atom, a helium atom. That releases a tremendous amount of energy. In fact, if I remember correctly, it releases, oh yeah, that's right, it was like a bucket full of hydrogen atoms jammed together will make half a bucket of helium, and it will also produce enough energy to heat or to power the entire North American continent for the next 100 years. It's pretty amazing. Now, what does this actually look like? I scoured the internet trying to find a nice, straightforward animation without it being too complicated, but also being accurate enough. And I think I found something here that might help. I'm just going to pull this back and begin at the beginning here. These little red blobs are hydrogen atoms, and as you can see, they're colliding with each other. And when the two protons hit, that ends up creating helium atoms. Now they're just pulling away from that star, so you can see it a little bit further back. If I pull this back one more time, you can see the hydrogens are hitting each other, the two protons are, and then they create a helium atom from that process. Tremendously powerful. But we do know that stars will eventually run out of hydrogen. There's only so much hydrogen in our sun, for example. And if you recall from the video or from our discussions, when our sun runs out of hydrogen, and you can write that along the next line here, something interesting happens. And you'll notice that the next circle over here along the arrow is a bit bigger than the one over here. And you might be able to anticipate when our sun runs out of hydrogen, it's not just going to sit there, it's actually going to expand and become a giant star. And giant stars, this is interesting. Giant stars are bigger, obviously. They're cooler than like the original star temperature, and they become much brighter. And there's also a color change. So when our sun becomes a giant, it will expand, the temperatures will drop down, it will become much brighter, and it's going to shift and become more orange or more red, which is all pretty crazy. But what's triggering all that? What's making the star do that? And the real trick here is that it's taking the leftovers, the helium that's left over from that star fusing hydrogen, and it's turning that into a fuel now. And it's putting 3 heliums together, making, well, this familiar atom right here, carbon. And that produces energy. Now, what would this look like? Well, I found a video clip that I think will kind of do the trick for us here. If we zoom in on this right here, the Earth is just minding its own business, and in about 5 billion years, the sun will begin to expand. And you can see it's enveloping right there. There went Venus. And as it gets closer to the Earth, of course, the temperatures increase, the solar wind becomes pretty intolerable, and eventually it's going to swallow up the Earth. And when it does, all of the atoms that make up the Earth, including all the atoms in the room with you right now, all those atoms are going to become part of the sun. Oh, I can't watch. Look away, children. So, What happens next? Once it runs out of helium, the star cannot fuse anymore. Now you might say to yourself, oh, Mr. Rogers, why doesn't it just use the carbon? It did that with the helium after all. Just use the carbon, jam the carbon atoms together, and you can stay alive even longer. The problem is that you need a lot of pressure to force these carbons together. I mean, you've got 2 protons in here. You've got 6 in here. It's much harder to put an atom together that already has 6 positive protons, and you try to jam another 6 positive protons. And you know what happens with magnets when they're both positive. They don't really want to come together. And so a star that was bigger than this might be able to get away with putting the carbon together to make even something bigger and make more energy. A 1X star doesn't have that luxury. It's not big enough. So what happens at that moment when it can't fuse anymore? Well, that's when you get the nova phase. It's not really an explosion, but it's pretty catastrophic. Huge layers of the outer parts of the sun are expelled into space, and the core, of course, collapses down and shrivels up. All of the rest of the planets become incinerated, burned to a crisp from an explosion like this, a nova. And ironically, nova is a Latin word for new, because when we first started seeing these things, other stars dying in the sky, they became very bright. We thought, oh, it's a brand new star. In actuality, it's a star that's dying. Kind of sad. So that's a nova. That's what our sun is anticipated to do. But what about the core? What happens to the core of our sun? Well, the core is going to collapse down. You might already know what it's going to collapse down to. It's got so much gravity. It's going to shrivel down until it's about the size of the Earth. And there's a name for that. Now I'm wondering how many people just blurted out the name out loud. I bet a couple of you did. Here it is right here, my friends, white dwarf star. That's what our sun is destined to become, a white dwarf star. It's a dead star about the size of the Earth. It's very hot. If you remember from the HR diagram, white dwarf stars are very hot, but they're not very bright. They don't shine anymore. And now you probably understand the reason. They're like the dying embers of a fire. And so it just slowly cools and cools until finally that white dwarf goes dark. Now what about the outer shell? Now here's something interesting. The outer shell will get expelled back out into space, and it'll become a new nebula. Now I've always thought it's interesting. Stars begin from nebula. Stellar nursery is a giant cloud of gas that pulls together under gravity and forms a star and forms planets. And here we are at the very end where we began, with a nebula again. And that's the beauty of the stellar life cycle. It's literally cycling around because the end is the beginning, and the beginning is also the end. This nebula that's formed from this star exploding, and you can see the white dwarf at the center of this nebula right here, all this gas will be expelled into space and will one day become a new solar system, and the cycle begins anew, as they say. Now you might be saying to yourselves, okay, all right, I kind of get that, but where are you on this chart right here? If you recall, what we've just done is the 1x cycle. So you started with a stellar nursery, you wrote in 1x here. Of course, it's a main sequence star right here with the hydrogen fusing together. When it runs out of hydrogen, it's going to become a giant star fusing helium, 3 heliums together. When it cannot fuse that together anymore, you get a nova explosion. The core will become a white dwarf star, and the outer shell will become a new nebula, which of course leads you right back where you started. Now you might be able to anticipate where the 2x story is going to go and where the 3x story is going to go. But in the meantime, I'm going to give you just a little bit of a break. We're going to pause, and we're going to come back, and we're going to get through the 2x a little quicker, and the 3x is going to go even faster than that. So I'll see you all in just a couple minutes.